Hello, everyone. We're working through statistical methods for rates and proportions, chapter 6, section 6.3. In this section, we're going to be talking about the odds ratio and its logarithm. So when we look at the odds of B occurring when A is present, we're really looking at the ratio of the probability of B given A divided by the probability of not B given A. All right, so we're going to create our data set that is discussing maternal age and the birth weight of the babies. And we can look at the table to see that we are in the same setup as table 6.1. And we could create PT, which is the joint proportion table, right? So this tells you the joint proportion of not being in A and not being in B is 0.675. So in our case here, remember that not being in A is a maternal age over 20 years, and not being in B would be a birth weight over 2,500 grams. So essentially 68% of our sample has mothers that are over 20 years old and have birth weights of their babies over 2,500 grams. We can define each of these cells' proportions as P11, P12, P21, and P22 using the square brackets, picking off of P dot T. So we remember have the rows, comma, the columns. So the first row, first column, that will give us P11. The first row, second column will give us P12. The second row, first column will give us P21, and the second row, second column will give us P22. Run that in. We then can get the marginal proportions, P1 dot, P2 dot, P dot 1, and P dot 2 using the apply function. So remember in the apply function that this second piece will tell us whether or not you're doing this to the rows or columns. 1 is for rows, 2 is for columns. In this case, we're taking the sum of the proportions. So I'm getting the row sum here. And since I want P1 dot, I'm going to pick off the first element. So if I just run the apply function, I get 25% and 75%, but P1 dot we know is the 25%. So I'm just picking off the first element, and P2 dot is the second element. Similarly, if I do the apply function on the columns, I'll have two proportions, and I can use the square bracket to pull off the first proportion or the second proportion to get P dot 1 and P dot 2. From here, I can also get the N dot dot, which is the overall sum of the table, and I can get the individual cell frequencies by picking off each of the pieces of my original table T. All right. If I want to look at the probability of B given A, that is P11 divided by P1 dot, and P of not B given A would be P12 divided by P1 dot. These are similar to the equations in our book. And then I can get the odds of A, similar to equation 6.6 of our text, by dividing P11 divided by P12. Essentially, the P1 dots cancel out when you look at the odds, and you can simplify the equation. I get 25.25. Okay, We can also get the odds of not being an A from equation 6.9. Once again, it's reducing to P21 divided by P22 because the P2 dots divided by one another end up being 1 and the equation reduces. All right. We can go on using 6.11 to calculate different measures of associations. One is the odds of A minus the odds of not A divided by the odds of A plus the odds of not A. That's 6.11 in our textbook, equation 6.11. We get 0.384. And we can calculate Y, which is given in equation 6.12 of our book as another measure of association, 0.2. And the main association that we're going to look at is the odds ratio, which is just the ratio of the odds. So we're going to get odds of A divided by the odds of not A. This is giving in equation 6.14 of our text. We get 2.25 as the result. And so what does that 2.25 actually represent? This is the odds of a young mother delivering an offspring with low birth weight being 2.25 times more likely than an older mother, right? So in this case, we might also want to get the standard error for the odds. And the reason for this is so that we could end up making confidence intervals and doing hypothesis tests covering the odds ratios. So the standard error of the odds is presented in equation 6.19 of our text. And we can calculate that standard error to be 1.004. And in our text, they also give us a modified version of the odds and the standard error, O prime and the standard error of O prime. These are given in equation 6.20 and 6.21. All right, you use this whenever you have any of your cell frequencies equal to 0. Okay. Essentially, we don't want to have anything that has to divide by 0. So we're just adding 0.5 to make sure that essentially we reduce the bias and we make sure that nothing is undefined. And the next portion we're going to go to is discussing the relative risk. And the relative risk is defined by the probability of B given A divided by the probability of B given not A. So relative risk is only similar to the odds in cases where the prevalence is very, very small. But in other cases, these really do measure different things. Okay, so when we calculate the relative risk, we can do this using equation 6.23. And in this case, we find that the relative risk is 2. Right, so the value here was not so far off of the value of the odds ratio. However, we should know that there are cases where the relative risk will be very different from the odds in its value. Okay, in this chapter, we go on to talk about the log odds ratio. And usually, if you are creating a confidence interval for the odds ratio, you'll actually start on the log odds scale, and then you'll exponentiate once you're finished. So first, you should know that in R, the default for the log is a natural log. Okay, if you want this to be log base 10, you would actually have to specify the base. So don't get confused here. This is a natural log. See, the base equals an exponential 1. So we know this is natural log by default. Okay, so first we can calculate the log odds being 0.81. We can also calculate L prime, right? Similar to equation 6.32. And that's the log odds prime, 0.818. We can calculate the standard error of L. We can also calculate the standard error of L prime. Okay, this is in equation 6.33. If you'd like to reference. Okay, so essentially here, I could end up creating a confidence interval by first looking at the log odds and using the standard error. And then at the end of the day, I would exponentiate the entire confidence interval. And that will guarantee that I get numbers in the space that I would like, rather than creating confidence intervals just based on our O prime and our standard error of O prime. So the general sense of what you're going to do is you'll start with the log odds ratios, and then you'll exponentiate at the end of the day. So I hope you learned something today, and that's the completion of section 6.3.